this video, we're going to talk about continuity. So let's first give the definition. A function f of x is continuous, or is said to be continuous at x equals a if the following conditions have been met. Here's three of them. The following conditions have been satisfied. The first one I'll call 1a. The limit as x goes to a to the left of f of x must exist. 1b. The limit as x goes to a plus of f of x must exist. Two is the limit as x goes to a from the left of f of x must equal the limit as x goes to a from the right of f of x. That means that the limit as x goes to a, that means it equals the limit as x goes to a, not plus or minus. And let's say that this common limit is L. And the last thing is that f of a must equal L. Now let us look at this and let's see how if one of them fails, then the limit doesn't, the function is not continuous at a. For example, if 1a doesn't exist, maybe it goes like that to infinity, and 1b is, the other side is very well defined. Okay, it just goes up like that forever. Okay, so if you're a little bit more than a, looks to me that the y value is going to that number. Well, whatever number that is. So 1b exists. Now 1a does not exist. This graph is not continuous for one simple reason. If I go to graph it, there should be a circle here. If I go to graph, well actually no, I take that back. If I go to graph it, right around here, I have to lift my pen to come here to continue. That graph is not continuous. And that type of graph failed 1a. Now, how can a graph fail 1b? Just look at the mirror image of what I just drew. You want 1b not to exist. Okay, so maybe at 1b, the function goes like this. So a little bit more than a, the limit's going to infinity. But for the rest of it, it's fine. Actually, it can have an open circle here. It's fine. But because it failed 1b, you can't graph this without lifting your pen. I have to lift my pen right now to go and continue. So that's where the graph can fail the graph cannot be continuous because it failed 1b. Now, what about failing 2? The left limit and the right limit, they're not equal. That's how you fail. Well, to the left of A, the graph can come up to get closer and closer to 7. And to the right of A, maybe the graph goes like this. And the y value is getting closer and closer to 9. This graph is not continuous, because if I try to graph it, right here I have to lift my pen to come here to the other points. That is how a graph can be not continuous if it doesn't satisfy 2. Well, what if it doesn't satisfy 3? But we try our best always to satisfy the others. So suppose we have our function like this. And here's our A. Trust me, that's an A. Okay, so let's see what happens. And let's suppose that point is 3. So the limit 1a, the limit from the left exists, because when I'm a little bit less than a, it looks like I'm getting closer and closer to 3. So 1a exists. From a little bit bigger than a, just a little bit bigger than a, I'm also close to 3. So 1a exists, 1b exists. And you know what? They both equal 3. However, f of a is not 3. L is 3 in this case. We said L was the common limit, and in this problem, the common limit was 3. Either f of a is not defined, that is, it's undefined, or maybe it's not this one, maybe it is, but I just updated it, and now f of a equals 4. But that's not the limit, that's not the L from 2. So those are the ways that a function could be, or a graph, which is a function, the graph of a function, it could not be continuous if one of these fail. If all of them pass, let us see what that means. If they all pass, here's A. The left limit, it has to approach some number, say 4. And the right limit has to also exist. But statement 2 says they have to be the same answer. So as I approach 2 from A from above, I have to get closer and closer to 4. As of right now, just having satisfied 1A, 1B, and 2, f of A doesn't have to be 4. Okay, nowhere does it say here from 1A, 1B, and 2 does it say f of A has to be 4. But if you're going to include 3, f of A has to equal that common limit. This graph must be continuous. And this is the reason I could remember this. I haven't written this down for decades. But I know it has to be true because, you know, how can the left limit and the right limit be different but the function's continuous? This say had to be wrong. This one has to come closer and closer to A. And then you have to fill it in, because limits don't care about what happened at A. You have to understand that. Okay. So let me state a theorem that I think is really good for a Calc 1 student to know, or any calculus student. We'll call it a theorem. Polynomials are polynomials are continuous everywhere. Continuous everywhere. Okay, and after all, a polynomial is just something that looks like this. Maybe it won't go up and down as many times as I drew. Maybe it would go up and down even more times than I drew. But nonetheless, that's what a polynomial looks like. And the key thing is I can draw a polynomial without lifting my pen. Polynomials are continuous. We're not going to prove that. Ask your teacher in class to prove it. Or watch my other videos on this channel where I prove theorems. Okay, so now this is a very big theorem when it comes to doing these continuity problems. If you're given that g of x is equal to x squared minus 3x minus 4 when x is less than 4, and it's equal to 3x cubed minus 9 if x is greater than 4. Well, first of all, let's see how to use this. I don't know why I was writing f, but if you wanted to find g of 7, so we have two rules for g. Which one do you use? Depends on the x value. The x value is 7. If the x value is less than 4, you use the top rule. The x value is greater than 4, greater than 4, you use the bottom rule. Since our x is greater than 4, we are going to use the bottom rule. 49 times 7, I guess, is 343. Minus 9 is 90. Yeah, it has to be 100 to 9. Oh, minus 9, 1020. Minus some silly arithmetic error. But the key thing is that to calculate g of 7, I use the bottom rule. Now, this theorem on top is very important, because if here's 4, it says if x is less than 4, I'm a polynomial. So here's this brick wall 4 at 4. I'm just a polynomial before 4. I'll put an open circle there. And I'm another polynomial when I'm bigger than 4. Now that other polynomial may pick up down here, or it may pick up from here. Now the question is, so what I know is if x is less than 4, this function is continuous. I know that. If x is bigger than 4, it's continuous. Okay? The question is why is it continuous? Because they're polynomials. The question is it continuous at 4? And of course the answer is g of x is not continuous at x equals 4. It's not even defined at 4. Even if the part that I'm erasing, even if the part that I was erasing linked up really nicely here, it's not defined at 4. At 4, we definitely have a circle there. It's not defined at 4. Okay, so now that one's done. let's just rename the function. New problem, next problem. You're given that h of x equals this, and just so it's very clear to everyone, I'm saying that x can equal 4 for the top one. So when x is less than 4, this graph is going to be filled in here. The question is whether or not this other graph, the one where x is bigger than 4, comes right here, or if it comes here, or anywhere else, or if it comes here. We just want to know if it's coming here. Okay, so we need to check 1a and 1b. 1a. If I'm going to use a and b, let me make sure I use the right sides, left or right side. 1a was from below. Okay. What is the limit as x goes to 4 from the left of h of x? Well, in this case, x may be really, really near 4, but it's less than 4, so I use the less than 4 rule. X squared minus 3x minus 5. And this is going to give me 4 squared minus 3 times 4 minus 5, which is 16 minus 12, which is 4, minus 5 is negative 1. Okay, that is 1a. Now, what is 1b? What's the limit as x goes to 4 plus? That means bigger than 4. This means bigger than 4. So I use the bigger than 4 rule. I use 3x cubed minus 9. And I get 3 times 4 cubed minus 9. I get 3 times 64 minus 9. And this is going to, if this were 8 and you took away 9, you'll get negative 1. You have two options. You can say it's not negative 1. I would accept that. Or you can bother to figure it out. 64 times 3. 3 times 60 is 180. Plus 12 more is 192 minus 9, which is 183. Not sure why I put 8. And then I would say that's not negative 1. So h of x is not continuous at x equal to 4. It's continuous everywhere else because this less than 4, we're a polynomial. Bigger than 4, we're a polynomial, and polynomials are continuous everywhere. But they just may not, the two polynomials may not link up very well. It turns out that it goes to 183. So, way, way up here, you have 183. And let's get rid of this piece. Let's get rid of this piece and that piece down there. So the top one says that it can equal 4 when you're less than 4, less than or equal to 4. And when you're bigger than 4, you have to get closer and closer to 183. Although this portion is continuous, this portion right here is continuous on its domain, less than or equal to 4, and this function, being a polynomial, is continuous on its domain, x bigger than 4. If these 2 points are in the same place, you got it. It's continuous. And it's defined at 4. Okay. This one, when it was g of x, where I didn't have equal to 4 up here, immediately, and I don't have equal to 4 in the bottom function, no way is it continuous at 4. But it's continuous everywhere else. And when I changed it to h of x by putting the equal sign right here, now it's less than equal, then we had to check. I had to do all this work to decide that, nope, it's not continuous at 4. It's not continuous at 4. When we didn't have the equal sign at x equals 4, that is, it just said x less than 4, not less than equal, this is all the work we had to do. It's not continuous at 4 since g of 4 is undefined. How on earth can undefined equal the common limit? That would not be possible. And I'm sorry that I went, let me just see something. Okay, I'm not sorry. I was going to say I'm sorry from using A's to C's, but I didn't. I actually went to using 4. Okay. Let's look at another function. Let's call it f of x. And f of x is a piecewise function. You have 3x plus 5. That's one rule. Another rule is x plus 1. And the third rule is x cubed minus 293. My goodness, which rule do you use for f? Well, they have to tell you. You use the top rule if x is less than 4. You use the bottom rule if x is bigger than 7 or equal to 7. You use the middle rule if x is between 4 and 7 and equal to 4. Now, again, this is a polynomial. Fine, it's a line, but it's also a polynomial. 4 and 7. Now, when you're less than 4, maybe the line goes like this. And since it doesn't say equal, I have an open circle there. Now, between 4 and 7, I am x squared plus 1. Well, x squared plus 1, well, that's 5. It looks like this. This is x squared plus 1. But I only want it between 4 and 7. Oh, why didn't you say so? So I only have this portion. It can equal 4, but not 7. Okay, it can equal 4, but not 7. And then I have this cubic above 7. And it can equal 7. So maybe it goes like that. Okay? Now, everywhere on the domain less than 4, the line is continuous. Everywhere between 4 and 7, x squared plus 1 is continuous. Everywhere bigger than 7, this cubic is continuous. The question is, what happens at 4 and 7? Was I mistaken? Maybe this part that I'm putting in green now, maybe this part that I'm having in green really should have been right here. So it filled it in. Maybe this point down here should have been up there and it got filled in. I don't know. I don't know. This is what we need to investigate. This is all we need to investigate. What happens at 4 and 7? Okay. What happens at 4 and 7? Okay. So, let's look at it. Now, notice that when it comes to x equals 4, this isn't anywhere near 4. So let's just number the equations, 1, 2, and 3. So around x equals 4, we're going to look at the limit as x goes from 4 below. And if you're less than 4, you use 3x plus 5. And we're also going to less than 4. And then we're going to look at the limit as x is a little bit more than 4. That's the middle function. It allows x to be greater than 4 and equal to. But I don't care about equaling 4. I don't care about equaling 4. So we have x squared plus 1. And we directly substitute 3 times x plus 5. That's 12 plus 5. That's 17. We directly substitute. We get 4 squared plus 1, which is 16 plus 1, which is 17. That tells me that the first 2 parts of the graph actually link up. The leftmost one, it ends right at 17. But it turns out that this quadratic picks up, this quadratic picks up right here, right at 17. And here is the quadratic. And it can equal 7, so we put an open circle there. So what we now know is f of s, because these two limits are equal, and, let's look at this. So what is f of 4? If x is 4, we use this middle function because it says x can equal 4. So you get x squared plus 1, which is 17. All 3 of these are equal. F is continuous at 4. F of x is continuous at x equals 4. Now, what about at x equals 7? What is the limit as x goes from 7 to the left of f of x? And what is the limit as x goes to 7, but from above 7? So let's find out what the function is. If you're a little bit less than 7, well, you use this function if you're bigger than 7. You use the middle function if you're between 4 and 7. That means if x is between 4 and 7. That means if you're less than 7, you use x squared plus 1. You get 7 squared plus 1, which is 49 plus 1, which is good old 50. The limit as x goes to 7 plus, if you're a little bit more than 7, x is more than 7, you use this rule. X cubed minus 393. Well, 7 cubed minus 393. 7 cubed is 343. Ooh, you take away 393 and you get 50, but it's negative. These are not equal. This was 1a, and this here is 1b. They exist, But step 2 says they have to be equal. Step 2 says they have to be equal. So this is not working. This is not working. So we conclude that f of x is not continuous at x equals 7. F of x is not, as opposed to non, is not continuous at x equals 7. Another name for not continuous is discontinuous at x equals 7. Let us look at another function. Piecewise functions. These are the ones you're going to see where they talk about where a function is continuous or not. Suppose the function is j of x, and it equals to x squared plus 1, but only if x is less than or equal to 5. Or it's 5x plus 1. This is when x is bigger than 5. I have one typo here. No less than equal. 5 is less, x is less than 5, or x is bigger than 5. At this point, I would say function is not continuous at 5. But there's more. There's more. It equals to 2x plus 4 if x equals 5. Okay. So now we can find j or 5, because we have a rule for the j function when x is 5. Okay. Again, polynomial is continuous if x is less than 5. Another polynomial, fine, a line, but that's a polynomial, is continuous when x is bigger than 5. And doesn't really matter what this is. It's really just a constant. It's only when x is 5. 2 times 5 is 10 plus 4 is 14. I could have just said that j of x equals 14 when x equals 5. It's just one point. A point is never continuous or not continuous. Okay, so we have this. And again, if you wanted to graph something like this, you have 5, you have something less than 5, you have something bigger than 5, and you have something at 5. You want to know if these 3 points are the same. Are they the same y value? Okay, so 1a. What is the limit as x goes to 5 of j of x? 1b. What is the limit from the left, as x goes to 5 from above of j of x? And 2 is whether or not they're equal. Well, this is the limit as x goes to 5 minus, well, if you're less than 5, that's what the minus means, you use this rule. X squared plus 1. So you get 5 squared plus 1, which is 25 plus 1, which is 26. So 1a exists. I know it exists. We found out what it equals. This is the limit as x goes to 5 plus. That means x is more than 5. If x is greater than 5, you use this rule. 5x plus 1. Ooh. So now we plug in 5 for x. 5 times x plus 1. 25 plus 1. 26. They're equal. They are equal. That is, in terms of our graph, I do know that I can update one thing. This graph bigger than 5 comes right there. Okay? And this check mark, that is the fact that these two are equal, that's number 2. Now number 3 is whether or not the limit is equal to f of 5. Is the limit equal to j of 5, excuse me. And when x is 5, I use this rule. I get 2 times 5, which is 10, plus 4. 10 plus 4 is 14. 3 failed. 1 passed, 1A passed, 1B passed, 2 passed. Condition number 3 failed. Why did it fail? Because this height is 26, and this point, when x is 5, is down here at 14. All I had to do was say that instead of this being 14, I just had to say it's 26. And then this point would go right there, and it would have been continuous. But the way it stands, it's not continuous. You just need to know these rules and go by them. Let's try the next one. Suppose you have that k of x, just a name. Sometimes it's 3x plus 1, and other times it's 2x plus 5. The top one is only when x is less than negative 10, and the bottom one is when x is greater than negative 10. Right away, you should, well, this is a polynomial, so it's continuous when you're less than negative 10. Every number less than negative 10. Here's a number line. I know it's continuous for all the numbers less than negative 10. And this is a polynomial, and it's continuous when x is bigger than negative 10. The only question is what about at 10? Now, since as of right now, I'll change it in a moment, but as of right now, it is not even defined at 10. You know, maybe not, but maybe, so here is negative 10. Maybe the left limit comes here, and the right limit come there. So 1a is satisfied, 1b, because it exists, 1b is satisfied, 2 is satisfied because they're the same limit, but 3 failed because whatever this common limit is, call it L, 7, 14, negative 2, well, not negative, pi over 3, the square root of pi, whatever L is, f of negative 10 is not L. In fact, it's not even defined. But we're going to take care of that right now. And we are going to put an equal sign there. That means that the left graph, which I drew like this, it actually filled this in. Okay, so the only place where this graph may not be continuous is at 10. Okay, negative 10. So we need to verify what we need to verify. We need to verify that the limit as x goes to negative 10 from the left of k of x exists, that the limit as x goes to negative 10 from above of k of x exists. And if we find out what it is, then we know if it exists or not. If you're a little bit less than negative 10, you use this rule, 3x plus 1. So you get 3 times negative 10 plus 1, negative 30 plus 1, negative 29. And this is the limit as x goes to negative 10 from above of k of x. Well, if you're bigger than negative 10, you use this rule. 2x plus 5. So you get 2 times negative 10, which is negative 20, plus 5. Negative 20 plus 5 is negative 15. These are not equal, so number 2 is not satisfied. 1a is satisfied because the limit exists. I know it is. We figured out what it is. 1b exists because we figured out what it is. 2 exists if and only if these two numbers are equal. And I want that to be the easiest one to determine. No, they're not equal. Okay. Let us try another one. Suppose you come to know that f of x, sometimes it's 1 over x, and other times it's 2 plus x, and it is 1 over x if x is less than 0, and 2 plus x if x is greater than or equal to 0. Now, this is a polynomial, so it's continuous when x is greater than or equal to 0. This is 1 over x. 1 over x, you should know from pre-calculus, it looks like this. Okay, but we don't care about when x is 0 or above. So I don't care about what happens here. Here x is 0 or above. The x value is 0 or above. I only care about less than 0. And, you know, I can graph this without lifting my pen. Goes to the right forever and ever. It keeps getting closer to the axis. X can get closer and closer to 0. This point right here, maybe it's that x value. I'm going to keep getting closer and closer to 0 by getting closer and closer to this y-axis. Okay, it's continuous. I can draw it without lifting my pen. So, once again, we have two continuous functions. The only place that they may not be continuous as a whole function is where they match up. They link up at 0. Okay, so we compute the limit as x goes to 0 minus of f of x. We compute the limit as x goes to 0 plus of f of x. This is 1a. This is 1b. If x is, I mean to write the limit as x goes to 0 minus. And if f of x when x is less than 0 is 1 over x. And here is going to be the limit as x goes to 0 plus. And if x is a little bit more than 0 or a lot more than 0, we use 2 plus x. Now this limit on the bottom will be 2 plus 0 or 2. This limit, well, it's going to be positive 1 over 0, but it's going to be negative. And a positive over a negative is negative. And if you have a number, whether it's 4 or 1 or 41, and you divide it by a really, really small number, you divide it by a really, really small number. That's a small number. The rule for dividing, if one of the two numbers or both of the numbers are fractions, is you keep the top number, you change division to multiplication, and you flip over the bottom number, which is going to be this really big number. And 41 times that big number is one big number. And if you say, it's not that big, fine. I'll make this number even smaller. I'll make this number even smaller by putting some more zeros. Okay, now 1 over whatever that bottom is, 1 over this really, really large number, well, it becomes 41. Keep the top, change division to multiplication, and flip over this number. Well, it's just going to have some more zeros. I'm not going to count that I put the right number of zeros. But the bottom line is it's going to infinity. And since the top is positive, and if you want to put 1, go for it, and the bottom is close to 0 but negative, positive over negative is negative. It's going to negative infinity. Okay, these are not equal. So f of x is discontinuous at x equals 0. In fact, it was enough just to show this. Equaling negative infinity, that means that limit doesn't exist. Negative infinity is not a real number. But I just went one more step. Okay. Now, I'll give you some graphs, and we're going to decide which ones are continuous and which ones are not. Suppose you have this graph. Let me draw the axes in a different color. Of course, x and y. X and y. So the axes, as I'm sure you know, maybe you never thought about it, but they're not part of the graph. If they were, then no graphs would be a function, because if this were part of the graph, it failed the vertical line test. That would make everyone's life easier, because then we would never study functions. Okay. So how about the other color is the graph. The other color is the graph. The instructions are which functions are continuous. This way we can talk more intelligently about it. When I say number 5, for example, you will know what function I'm talking about. Number 1 is continuous because I can clearly, hope it's clear, I can clearly draw this without lifting my pen. Number 2, remember, everything for graph number 2 is what you see, but not the green axes. Okay, to graph everything, you're going to have to come here, lift your pen to go there, and then go here. I mean, I'm not going to argue that you're right, that you could have just done this piece first, and then lift your pen and graph this piece, and then come down there and graph that piece. Okay? But you have to lift your pen. This is discontinuous. This function is only defined, like if this is A and this is B, it's only defined from A to B. It can equal B, but not A. I can graph this without lifting my pen. I just did. It is continuous. Don't worry about the endpoints. Now, okay, let's talk about that comment a little bit more. If they tell you that this is a domain, it's open at A and is closed at B, then it's continuous. So let's actually go back to a couple of other graphs. This has arrows. This has arrows. And we have arrows here. Okay. Number 4 is continuous because I can graph it without lifting my pen. Okay. This is continuous. This one, number 5, is not continuous because, for example, I have to come up to here, lift my pen, and continue there. I had to skip that point. So, it is, I had to lift my pen, it is discontinuous. Number 6 is discontinuous because right here I have to lift my pen to go there. Discontinuous. That completes this section on continuity.